everyone, myself Bhagyesh Kasle. In today's session, we will talk about the modal analysis. So, before starting with the modal analysis in the ANSYS, let's talk about or let's go for some story. Okay? In 1940, there was a bridge in Washington. It was built in 1940, and after the building of that bridge, after the 3 months after that inauguration of that bridge, one day the bridge was collapsed. Now what happened in that case? In one of the morning there was some storm. So initially the speed of the wind was less, right? At that time the bridge started shaking, and then after that, once the speed of the wind gradually increases, the bridge started shaking, and after that it was collapsed. Now there was a problem. There was a question for the designers why this was happening, right? So the whole study was carried out, and after that the conclusion was drawn that the reason behind the collapse was nothing but the resonance. Now what is the meaning of resonance? Now consider any body in the universe. Now what happened? Each and every body in the universe has its own frequency that we are calling it as a natural frequency. Okay, now what happened when the excitation frequency that has been caused by another agency, if that external frequency, if excitation frequency matches with the natural frequency of the body, at that time the resonance occurs. So resonance means what? At that time the displacement will be the maximum, right? Now we will try to understand what is the modal analysis. Now modal analysis is nothing but the vibrational analysis. Now the question will be like this: why we are calling it as a modal analysis, right? So when we are in the school as well as when we are in the college, at that time we have done an experiment. So experiment was like that: there was two poles, okay, and between these two poles the string was attached. The string was tied by the two poles, right? Now what we used to do, we have a tuning fork with us, and we used to strike it on the pad, and then we used to touch it to the pole. Once we touch the fork to this pole, what happens? This string will start vibrating, and initially the shape of the spring will look like this, right? Okay, now what happened? See, if now we used to perform this experiment in the groups, right? So one of the student from the groups, what he decided, okay, I will strike that tuning fork with some extra force, right? So harder way, okay. Then what he has done, again he has strike with so much energy, and again he has touched the fork to this pole. Now what happened? The string is vibrating like this. Okay. Initially there was only one loop, now there are two loops. So once we gradually increase the frequency of the tuning fork, there will be more number of loops there, right? Now what happened when the first loop was occurred? This was the loop. Now this distance will be maximum at the center, right? So how many distances will be there? Only one displacement will be there, that is the maximum displacement. That's why it is called as the first mode. Okay. Then if we gradually increase the frequency, then there will be two maximum displacement. One will be occur at this point, that is in the 1/4 portion, and second will be occurring at the 3/4 portion. This is called as the second mode. Now in our analysis, we used to find out the different modes, and we will use to find out what is the behavior of that object at that particular mode, right? So let's go to the software. Okay, now let's talk about the how to perform the modal analysis in the software, right? So we have opened the workbench. We have a version that is a 19.2 version, and in that we are going to perform the modal analysis. Okay, now to perform the modal analysis, we have a analysis system called as a modal. So just drag and drop this modal system into the project schematic. We'll consider a simple example. Okay, so what we will do, first we have to create a geometry over there. So simply right click on this geometry, go to the design modeler. Okay, so let's set the units to millimeter. So go to the units and click on the millimeter. Okay, now for this modal analysis, we will consider a simple example of a cantilever beam where one end of the bar will be fixed and another end of the bar will be free, as we have to calculate the natural frequency of the bar. Okay, so let's go for the modeling. So simply right click on this XY plane and say look at. Okay, now to create a bar, we will create a simple rectangle and then we will extrude it. So simply draw a rectangle. Now we'll go to the constraint. Right now all the lines are horizontal and vertical, so no need to do it again. Simply we will put a symmetry constraint over there. So simply click on the symmetry, select the axis and then select the sides. Okay, then again we have to perform the symmetry option. So right click on that and say select new symmetry axis. Now select the horizontal axis, first side and then the second side. Okay, the symmetry has been done. Now we will give the dimensions over there. So I will consider the dimension as a 250 and 10. Sorry, 50 and 10. Okay, now we will extrude it. So simply click on the extrude, select the sketch 1 and say apply. Then in the distance we will put the value as a 250 and then say generate. Okay, now it has created a simply supported beam. Okay, or I can say a cantilever beam. Okay, now let's perform the modal analysis on that. Okay, to perform the modal analysis, we have to go for the modal. That the model we are calling it as a mechanical. Okay, now this is nothing but the mechanical model. All the steps, that is including meshing, the boundary conditions, that is the setup part, the solution and the results we will perform in this model itself, right? So let's start with the material. Right now no need to change any material, we will use the structural steel as a default material, right? Now what is the next step? We have to go for the meshing. So right now I am doing the meshing with the default values. So simply right click on the mesh and say generate. Okay, the mesh has been created. This object has been divided into number of subdomain. That process we are calling it as a meshing, or in theoretical language we are calling it as a discretization, right? Now what is the next step? We have to apply the boundary condition on it. Okay, so what I have said, the boundary conditions for this object are the one end of the bar is fixed and the another end of the bar is free, right? So what we will do, we will apply a fixed support on one of the faces. So simply click on the model, go to the supports, fixed support, simply select the face and then say apply. Okay, the support has been set up, right? Only fixed support will be there and the other end will be fixed. Now we will try to find out just, okay, now how many maximum modes you want to find out. Just go to the analysis setting and in that you can find out the option called the maximum modes to find out, where we can find out the maximum number of modes and the behavior of the object for the particular mode. Okay, so I will consider 6 number of modes for that. Okay, the setup part has been completed, the boundary condition has been applied. Now we'll go to the solution. So like in structure analysis we have to consider the stress, the deformation, but in this case we no need to consider any stress or any output over there. Simply right click on this and say solve. Now the ANSYS is solving this solution. The solution part is completely automatic. No need to do anything for that. Okay, the solution has been done. Now if you observe the graph over there, you will find the 6 modes over there. So 1, 2, 3, 4, 5, 6, and besides that we can see a tabular data which will showing there's some values over there. So the table is containing the modes and whatever the frequency we have got, that has been included in that table. So we'll try to understand what is given in the table. Now for the first mode, the value of the frequency, it is given at 132.24. For second mode it is 635.83. Now what is the meaning of that? So for the first mode to occur, the frequency, the excitation frequency, it should reach the value of 132.24. So if the excitation frequency reaches at this value, the first mode will be occur. Now let's check out what happened in the first mode. So what is the displacement we are getting now, that we have to find out. So simply right click on this graph, say select all, again right click and say create mode shape results, right? So it will create a 6 modes over there. So 6 deformations are there. Okay, so simply we will click on the solve. Okay, so what happened? We have a first mode and for that the first deformation is there. Now what is the frequency value? It is 132.24 and at that moment we are getting a maximum displacement of a 64 mm, right? So what is the meaning of that? So how to interpret this result, right? So when the excitation frequency reaches at the 132.24 Hertz, at that time the displacement will be 64.045 and the behavior will be like this. So we will see the animation over there. So it will look like this, right? So this is the behavior of the object for the first mode. Similarly, we can observe the behavior for the second, for the third, fourth, fifth, and the sixth one. So if you observe all the modes, then we will see at mode number 4, when the excitation frequency is 121.8, at that time the deformation is maximum. So what is the meaning of that? The natural frequency of the object is nothing but 1211.8. Why? Because at that point the deformation is maximum and after that the deformation is decreasing. See, 64 and then the 62. Now as a design engineer, our task is to extend or to reduce or to increase this first mode frequency up to that natural frequency value. That means what? We have to change the design in such a way that the first mode will be occur after 1 to 11.8 Hertz. This is nothing but the modal analysis, and this is all about how to perform the modal analysis as well as how to predict the result in the modal analysis. Thank you so much.